All right, so now we're going to talk about tangent vectors to embedded submanifolds. And in particular, we're going to embed them into a vector space of some sorts, right? So we have a manifold M. It's like there's an inclusion map. It's like to a vector space E. Okay, let's say we have a gamma curve in M with the property that gamma at 0 is some point x, which is on the manifold M. Okay, and I'm going to define essentially it's like gamma prime at 0, right? And this is just going to be sort of the derivative. It's like, but we're using the linear space structure. It's like which comes from the embedding of M. It's like into the vector space E. Okay. So it's the limit as t goes to 0. It's like of gamma at t minus gamma at 0 over t. And really, what I mean by this is that I'm actually looking at the inclusion of gamma at t minus the inclusion of gamma at 0, right, divided by t. Okay? But I'm going to omit the inclusion, right, to simplify the notation. Okay, so so technically speaking, of course, it's like if you're just talking about these curves as being on M, it's like you can't really take the difference of those two things. But you know, M is embedded. It's like in this vector space. So if you take the embedding of, you take the inclusion, it's like into the vector space, then we can talk about differences. Okay, so if you see something like this, it's like it doesn't. It's not sort of clear what's going on. It's like you should sort of think that implicitly it's like using the inclusion. It's like into the vector space. Okay, so in any case, it's like this means that gamma prime at 0 is an element of the tangent space at x of the of the vector space, which I can again identify. It's like with the vector space itself. Okay. So if you have some sort of manifold, for example, right, you have a point x, which is gamma at 0, and you have some sort of curve gamma of t, right, then you think of this as being sort of the usual tangent vector to that curve. It's like where you view that curve as being embedded in the Euclidean space. Okay, in the vector space, sorry. Okay, so right, so there's this, and then there's, of course, it's like a gamma dot, right, which is this sort of abstract tangent vector, right, which is in the tangent space at x to m, right? And this is because, of course, gamma is a curve on M, so it induces a tangent vector. It's like this abstract tangent vector, it's like which is in the tangent space at x of M. And it's in tangent space at x because gamma at 0 at time t equals 0 is equal to x. Okay. So, all right, so there's formally two different things. There's gamma prime and there's gamma dot. It's like the question is how these things are related to each other. So how are gamma dot and gamma prime related to each other? And you expect, of course, that they be closely related to each other. Okay. So let's see what happens. Okay. So, so if you recall, it's like this abstract tangent vector is defined by its action on a function, right, which is defined in the neighborhood of the point x on the manifold, and it maps that function to a real value. It's like, and again, intuitively, it's like that action is through this notion of a directional derivative. Okay, so let's see how these things are related. Okay, so if f bar is a real valued function, okay, in a neighborhood u of x, in the vector space E, and F denotes its restriction, of F bar, right, to the intersection of U with the manifold M, right? I mean, technically U intersected with the image under the inclusion, it's like of M, but anyway. Then we have the following. Okay, so what's going on here, right? So what's going on is that another way of thinking about it is that maybe you have a function f, it's like defined on the manifold M, right? And you can think of f bar as essentially an extension of that, a smooth extension of that function into the neighbor, into the vector space, which M is embedded in. Okay. Then gamma dot, it's like acts on f. It's like because we think of these abstract vectors as being essentially derivations. It's like so these act on functions and they satisfy the satisfy a sort of a Lipschitz, it's like property, and then right, and we want to compare it, it's like to how maybe gamma prime acts on f bar. Okay, so what we have is the following. So gamma dot 0 acting on f, right, is by definition, right, the time derivative evaluated at t equals to 0 of f applied to gamma of t. Okay, right, and we can do this because gamma is a map from the rails, it's like to the manifold, f is a map from the manifold to the rails, so at the end of it, this is a map from the rails to the rails, so you can take the derivative as per normal, and then this is equal to d dt, again evaluated at t equals to 0, of f bar applied to gamma of t. And the reason, of course, why you have this is because on M, it's like f and f bar agree with each other, right? And gamma of t is in M. Okay, so you have equalities here. So throughout all of this, you know, there's an inclusion map of M. It's like into the Euclidean space, which is floating around. So technically speaking, it's like when we do this gamma t, I have to take the inclusion of it to get me into E, where f bar is defined. But you know, again, I'm dropping this for simplicity of notation. And then this thing, right, is now everything here is can be expressed in terms of the usual differential of f bar of x, and then this is in a vector, right? So this is gamma prime now of 0. Okay, so this I can write down. This is the usual notion of the derivative. It's like, or differential. It's like of a function. It's like acting on a vector, and since everything here is in Euclidean space, it's like it just sort of uses the classical definitions of these things. Okay. Okay, so this is basically how these two things are related, right? It says that gamma dot, which is this abstract vector acting on F, is really obtained by looking at this, you know, derivative or tangent vector to the curve. It's like in the embedding space, defined classically, right? And then the linearization of the sort of the extension of the map F into some neighborhood. And the whole point is that this doesn't depend on the extension, it just depends on F itself. Okay, so the extension is this F bar, which we're talking about. Okay, so in any case, so this yields the following. A natural identification. Yeah, so I should say, yeah, sorry, no, what I think I earlier had said sort of Lipschitz. What I should have said is that the abstract vector can also be, the abstract tangent vector can also be viewed as a derivation, right? And derivation is a linear operator. It's like which, you know, it's like satisfies the Leibniz rule, right? Okay, which is right. Anyway, okay, so this yields a natural identification of Txm, right, with the set given by gamma prime 0, so gamma is a curve in M, and then gamma at 0 is X. Okay, so you identify, excuse me, identify the tangent space at X. It's like of a manifold M. It's like with essentially the tangent vectors where you take all possible curves. It's like in M, you embed it into the Euclidean space. As long as you have the property that the curve, it's like at time 0 is the point X, right? Because you want to look at the tangent space at the point X, and then you differentiate that embedded curve. It's like to give you a tangent vector, right? So this is really in the tangent space to, so if you recall, this thing here is in the tangent space at X, right, to the Euclidean space, okay? Okay. So this is basically the picture it's like we have in mind, right? So if you imagine you have a manifold M, you have a point X, right? And you can imagine that M is again embedded via some inclusion. It's like into a vector space, right? And so when I keep drawing pictures like this, right, that this is Tx of M, right? That tangent space, right? When I draw it this way, you should think of it visually as being a subspace of, you know, it's like the embedding space, right? So, and then of course it's like that tangent space to the manifold M is spanned by, you know, it's like a basis, right, which consists of vectors. It's like of dimension of the embedding space, right, and then they're going to be the number of those. It's like basis vectors is going to be the dimension of M, right? So that's perhaps sort of not too surprising, okay? So yeah. Anyway. Okay. Okay. So yeah, so I think it's you know, for the purposes of your intuition, it is oftentimes helpful to think of this manifold as being embedded. Of course, that's not necessary. And if you don't have an embedding inside of the manifold, then you have to appeal to this notion, this more abstract notion of a tangent vector. It's like where you think of it then as a map from scale-valued functions to the reals, right? Okay, so in any case, the point is that there is this identification between gamma dot, which is this abstract vector, with gamma prime, which is, you really should think of it as being the literal tangent vector, where you take the representative curve, it's like, and you embed it, it's like into the into the embedding space. So we can think of these, and so in view of this identification, of TXM with this set here, right, we will now write gamma dot, gamma prime, and ddt gamma of t interchangeably. Okay. Okay. So yeah, so there's this identification. It's like which you should think of. It's like at the back of your mind, right? But again, it's like if you're just dealing purely with abstract manifolds, it's like where you're not assuming that you have an embedding. It's like then the one of the right ways of thinking about it is in terms of sort of this notion of a abstract tangent vector. It's like in terms of these maps from scalar value functions to reals. Okay. All right. So now let me sort of say something about a specific but important case of embedded manifolds, right? So so if M is defined sort of either locally or globally, right, as the level set of a constant rank function, okay, F which is mapped from say a vector space, it's like to Rn. Okay, then we have that df at x, sorry, okay, that the tangent space at x of M, right, is equal to the kernel of the differential, it's like of f at x. So this means that because C is a tangent vector to M, right? If df, it's like at x applied to C, right, is equal to 0. Okay. So how do we see that, right? So if, for example, gamma is a curve in M, right, with the property that gamma at 0 is equal to x, right, we know that f of gamma at of t, right, is equal to basically f of gamma at 0. Okay. Oftentimes we'll just say that this is equal to 0. It's like, but that's sort of predicated on the assumption that m is actually the 0 level set of f, right? So if we don't assume that if we don't assume that m is the 0 level set of f, it's like then we still have the property that it has the same value, right? It has constant f value, right? So f of gamma of t is equal to f of gamma at 0. And so when you differentiate that, it's like you still get 0, right? So in either case, so df of x applied to gamma dot of 0, right, is equal to d of f composed with gamma of t, right, dt evaluated at t equals to 0. It's like, and that is constant, so that is equal to 0. Okay. So that's the way you show that a tangent vector, it's like to m, it's like where m is viewed as the level set of this constant rank function f, right, is going to have the property that that tangent vector is in the kernel, it's like of the linearization of the map. And it just comes from the fact that for every point in the manifold, it's like the value of f on any point in the manifold is constant, right? So this composition f composed with gamma, right, is going to be constant. So its derivative when you evaluate at 0, well, its derivative in general is going to be 0. Okay, so that's how you check that. This really gives you an honest to goodness characterization of the tangent space here. Okay, so this means that obviously this means that gamma dot at 0 is in the kernel of df at x. Okay. So then you can check that basically these two things are contained within each other. They have the same dimension. You can check this through some sort of rank and nullity theorem type argument. And so this have to be actually equal to each other. Okay. All right. So let me just stop here for now.